AIs to help us retain information and put our best foot forward. Enter Speechify, a reading assistant.
You're just in my last class. Let's see how many of y'all. So most of y'all. Okay, cool. Well, for those of y'all that I didn't get to meet in the last class, my name is Allie. I just graduated from A&M with statistics and computer science, and I'm now, I don't think I said this last time, I'm now working for Capital One as a software engineer. And I was on the previous 2 years Datathon teams, so it's fun to be back. And so, this class is kind of a follow-up to the last class. This one's just all about machine learning, what it is, what it means to make a model for your data, how to make predictions. So we're going to go over that. If you are new to Colab, it's basically just Jupyter Notebook, but hosted by Google. So you get to make use of all of Google's resources and their cloud and shareability features and all that. So I believe if you go on to the Datathon website on the events page and you click on this event, you should see the collab that I'm going through, so y'all can have it up if you want. Make sure, I think it should be all set, but make sure you're not running from the same one I'm running from. Questions? Ooh, okay. Are you able to access the website and push it, or should I just send it to people? Uh-huh. Oh, this is different. This is for my class, like on the events page. Okay, let me try to get it to y'all real quick. Okay. Well, maybe this works. Yeah, except for this is going to be a real great way of doing this, but I'm just going to email it to myself and then use Discord on my phone because I don't know what my login is. Right. And what we're working in today, we're going to start with decision trees, which are really interpretable, and then random forests, which is like a modification of that. That's just a little more accurate. So we'll kind of discuss the like why they are, like why they fall, where they fall. Alright, so to start off with decision trees, I'm actually going to play a video from StatQuest. So if y'all haven't checked out StatQuest before, they have some really, really good videos. And so we'll go through a little bit of it. Not all of it.
StatQuest
I might make it faster too. So just give me a minute.
is growing up. StatQuest is growing down. StatQuest is growing. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to be talking about decision trees. Here's a simple decision tree. If a person loves StatQuest theme songs, then that person is awesome. And if a person does not love StatQuest theme songs, then that person is slightly less than awesome. In general, a decision tree asks a question and then classifies the person based on the answer. It's no big deal. This decision tree is based on a yes-no question. But it is just as easy to build a tree from numeric data. If a person has a really high resting heart rate, then that person had better see a doctor. And if a person does not have a super high resting heart rate, then that person is doing okay. Here's one more simple decision tree. This decision tree is based on ranked data, where 1 is super hungry and 2 is moderately hungry. If a person is super hungry, they need to eat. And if a person is moderately hungry, they just need a snack. And if they are not hungry at all, then there's no need to eat. Note, the classification can be categories or numeric. In this case, we're using mouse weight to predict mouse size. Here's a more complicated decision tree. It combines numeric data with yes-no data. Notice that the cutoff for resting heart rate isn't always the same. In this case, it's 100 BPM on the left side and 120 BPM on the right side. And the order of questions on the left side, first about resting heart rate, then about eating donuts, doesn't have to be the same on the right side. On the right side, the question about donuts is asked first. Lastly, the final classifications can be repeated. For the most part, decision trees are pretty intuitive to work with. You start at the top and work your way down and down till you get to a point where you can't go any further. And that's how you classify a sample.
Oh no, we're gonna have advertisements. Sorry,
Thank you for
to be
coming on such
continued.
short notice.
Oh no, jargon alert. The very top of the tree is called the root node, or just the root. These are called internal nodes, or just nodes. Internal nodes have arrows pointing to them, and they have arrows pointing away from them. Lastly, these are called leaf nodes, or just leaves. Leaf nodes have arrows pointing to them, but there are no arrows pointing away from them. Now we are ready to talk about how to go from a raw table of data to a decision tree. In this example, we want to create a tree that uses chest pain, good blood circulation, and blocked artery status to predict whether or not a patient has heart disease. The first thing we want to know is whether chest pain, good blood circulation, or blocked arteries should be at the very top of our tree. We start by looking at how well chest pain alone predicts heart disease. Here's a little tree that only takes chest pain into account. The first patient does not have chest pain and does not have heart disease, and we keep track of that here. The second patient has chest pain and heart disease, and we keep track of that here. The third patient has chest pain but does not have heart disease. The fourth patient has chest pain and heart disease. Ultimately, we look at chest pain and heart disease for all 303 patients in this study. Now we do the exact same thing for good blood circulation. Lastly, we look at how blocked arteries separates the patients with and without heart disease. Since we don't know if this patient had blocked arteries or not, we'll skip it. However, there are alternatives that I'll discuss in a follow-up video. Remember, the goal is to decide whether chest pain, good blood circulation, or blocked arteries should be the first thing in our decision tree, aka the root node. So we looked at how well chest pain separated patients with and without heart disease. It did okay, but wasn't perfect. Most of the patients with heart disease ended up in this leaf node. And most of the patients without heart disease ended up in this leaf node. Then we looked at how well good blood circulation separated patients with and without heart disease. It wasn't perfect either. Lastly, we looked at how well blocked arteries separated patients with and without heart disease. Note, the total number of patients with heart disease is different for chest pain, good blood circulation, and blocked arteries, because some patients had measurements for chest pain, but not for blocked arteries, etc. Oh no, it's another one of those ghastly jargon alerts. Because none of the leaf nodes are 100% yes heart disease or 100% no heart disease, they are all considered impure. To determine which separation is best, we need a way to measure and compare impurity. There are a bunch of ways to measure impurity, but I'm just going to focus on a very popular one called Genie. To be honest, I don't know why it's called Genie. I looked around on the internet and couldn't find anything. However, if you know, please put it in the comments below. I would love to know. Regardless, the good news is calculating Genie impurity is easy. Let's start by calculating Genie impurity for chest pain. For this leaf, the Genie impurity equals 1 minus the probability of yes squared minus the probability of no squared. Now let's plug in some numbers. The probability of yes equals 105 divided by the total number of people in this leaf node. And the probability of no equals 39 divided by the total number of people in this leaf node. After we've done the math, we get 0.395. That is to say, the Genie impurity for the leaf node on the left equals 0.395. Now let's calculate the Genie impurity for this leaf node, the one on the right. Just like before, it equals 1 minus the probability of yes squared minus the probability of no squared. And the probability of yes is 34 divided by the total number of people in this leaf node, and the probability of no equals 125 divided by the total number of people in this node. And if we do the math, we get 0.336. Now that we have measured the Genie impurity for both leaf nodes, we can calculate the total Genie impurity for using chest pain to separate patients with and without heart disease. Because this leaf node represents 144 patients, and this leaf node represents 159 patients, the leaf nodes do not represent the same number of patients. Thus, the total Genie impurity for using chest pain to separate patients with and without heart disease is the weighted average of the leaf node impurities. So to calculate the weighted average, we take the total number of people in the left leaf node and divide it by the total number of people in both leaf nodes. We then multiply that fraction by the Genie impurity for the left leaf node. Then we take the total number of people in the right leaf node, divided by the total number of people in both leaf nodes, and then multiply that fraction by the Genie impurity for the right leaf node. After we do the math, we get 0.364.
All right, we'll stop there. So yeah, I love playing that video because I think he just speaks so clearly and he makes it seem so easy. Like it's really easy to follow. You kind of understand what a decision tree is doing. You can follow the path and see why they're making the decisions that they're making and how they're scoring them. But in that example, they're using the Genie score, which they showed you the math behind. And what they would do is you go through each column and you try to think of each split that you could make, and you go ahead and you make it, you evaluate it, and that's how you build your tree. Is just continually going down and picking the next best thing that you can split by and seeing how pure of a decision that you can make from it. So decision trees, if we go back and see, I think it's just slightly, yeah, it's right here. So they're really interpretable, right? And that's for that reason. It's because you can follow the decisions that are being made and you can see why the computer picks what it picks. And so it's really powerful as a tool to just understand why it's doing what it's doing. And it scales like crazy because the examples that we saw, they were really looking at binary categories, right? It was either yes or no for all those things, for all the predictors. But it works just as well with numeric predictors. And so instead of just saying, instead of having a true false where like one direction is yes and one direction is no, it actually kind of creates bins with your numeric columns. And so it'll say like, if weight is under a certain value, and then it becomes binary. Does that make sense? So you can use the same thought process on columns that aren't inherently categorical by just creating categories from it. And so it becomes just a really, really powerful tool. And it's kind of crazy when you think about how many decisions you can make. Like say your data frame has like 20 columns even. The number of like options that you could have at every level of your tree is like insane, but it's able to calculate it and produce something that is really interpretable and also really powerful. So it scales really, really well. So I'll show you how to do some decision trees. And one of the most common algorithms right now that's out there is random forest. It is built on top of decision trees. So this is like the basis for what that does. Also, if you've heard of anything called like XGBoost or AdaBoost, like those are also even extensions on top of that. So this is really like where the root theory comes from, is with decision trees, and then people have optimized it doing other things. And we'll get to those too. But it's important just to understand like where that comes from. So this first example that we're going to look at is the iris data set. This is a data set that is built in to the Seaborn package, so we can just load it straight from there. If you're not familiar with Seaborn, Matplotlib, and Pandas, These are just really great tools that are built into Python. You import them with the syntax that's shown. And I can go ahead and I can load the iris data set. And I'm going to make a pair plot just to show you kind of an overview of what it looks like. Probably need to minimize it just a minute. But this data set, so it has a couple of different columns that describe attributes. It's all about flowers. So there are basically 3 different species of flowers. And I think each species has like 50 instances in this data frame or something like that, with different measurements for like sepal length, sepal width, and petal length. And the whole point here is we're going to be able to try to see if we can determine which of the species it is in based on the data. So you can kind of start to look here about relationships and how they're, even from the graph, like you can see, especially this blue one, it looks like it's really clustered. Like there may be a place that you could split it, right, to be able to identify like where the blue ones would be versus the others. So that's kind of what the decision trees will end up doing, right, is figuring out this. I'm going to use this graph as an example because I like how the blue is very far separated. But you might look at this and say, oh, like you could have a pretty pure score if you tried to split it with like length at 2 or 3, right? So that's what decision trees end up doing, is finding a place where you can really like cluster, like take your clusters out and have it pretty pure. So let me get it back up here. All right, so the first thing that you do when you model, let me make sure I ran this because I'm going to need it. Okay. Is you always have to split your data frame into your features and your target, or your X and your Y. And so in this case, my target is species because we're predicting what species of flower we're going with. And here are all the different features that we're going to throw in there to predict with. And I can split my data frame by the following. So these are now, it'll extract all the columns that are your features and your target, put them into X and Y for you. And then the great thing about Python is a lot of it is pretty repetitive, right? No matter what model you're doing, your syntax is going to be almost identical, which makes it really nice and really easy to switch out. So if you memorize it once, you're pretty much good to go, and you can just like swap models without too much work. So this is kind of what it's always going to look like, is that you end up importing whatever model that you're running, and then you fit a classifier. So you always instantiate a classifier first. And there's some parameters in there that you can alter. So random state is just kind of whatever seed you're seeding the model. Sometimes it does make a difference. So, and then in this instance, we're going to set a max depth, and just doing this so that it doesn't take as long. And so I can show you if the tree gets too big, then you can't really walk through it as much. So we're going to make a decision tree classifier. And then after you instantiate your model, then you fit it to your data. So the next step is to do clf.fit with your X and your Y data. And then you're able to see the results. So we're going to plot the tree, and this way I can show you guys kind of what decisions it was making and how it was doing it. So at the very top, it decided that the thing that would be the best was to do width less than or equal to 0.8. And it had a pretty high impurity. And so let's go ahead and look at that. So it says, what is it? Width less than or equal to 0.8. And it was, sorry, petal width. Okay. So here's the petal width, right? So less than or equal to 0.8, it's like right about here, right? That's pretty good, right? You can see like why it's picking that already, even just from the graph, because you can tell that if you drew your line there, you are distinguishing a class, right? So that kind of like I was talking about, that's exactly what it's doing. It's figuring out where can I draw boundaries to best separate it. So it's cool that you can now, this is why decision trees are really neat, is because you can see exactly why it's doing what it's doing, and it makes sense. So you could, like, if you were fitting a model and you had to go explain it to your boss or someone who's really not technical and you need to show them what it's doing, this is a really good one, because you could be like, yeah, like, this is why it's doing this. It just really makes sense. And so it keeps going. So I think, it'll just like build the tree based on true and false from that. It continues to evaluate what the next highest purity would be, right, from there, and continues to make decisions until you then classify. And so if we were to go and look and follow the other decisions that you would make, you could see that it would subsequently continue to choose areas on the graphs that would give you a good selection, right? It keeps finding different areas that you can cluster it by. And then you're able to ultimately predict, right? So if you fell into this bucket, you would predict this class versus this class versus this class. So that's how you end up making your decision. You just follow those paths. And these get it's interpretable, but it does scale. So like in a real model, your depth might be absolutely huge. So it follows a lot of different paths to ultimately get you to your decision. All right, now we're going to look at another example. I probably need to get it bigger for you guys. So this one, again, this is the Titanic data set. It's also built into Seaborn, so you can use it. And what we're going to do here is we're going to try to predict who survives. So we have a lot of different classes here, and got to do some data wrangling first just to make it in a format that we want. So for instance, we're going to add a column here we have to binary encode. So right now it's just male, female, but we really want it to be zeros and ones instead of male, female. So we're going to do that. We're also going to one-hot encode the classes. I believe in general with machine learning, it's good to not leave strings. You want things to be numeric. So you have to do some encoding to get it to have, instead of classes, you have numbers. So you can, if you just have two, if you just have 0 and 1, binary encoding is pretty easy because you can just do a Boolean and then do as type, and that'll convert it to 0, 1. If you have multiple classes or something more than 2, you really have to do get dummies, or there's some other one-hot encoding functions that do the same thing. But basically what it does here is so with get dummies, it actually will, for each class, it becomes its own column, and then true false within its own column, so it expands it out with one hot encoding. So your data frame gets bigger, but you have to have numeric values to feed into models. So that's how that works. And you also want to make sure before you do any type of modeling that you don't have a lot of null values, because that will just throw a wrench in everything you're trying to do. So in this instance, we're going to go ahead and fill our null values. And in the last class, when I talked about different methods of handling null values, I said that you could, for instance, if one of your columns is just almost all null, you probably just want to get rid of it. Just drop that column altogether. If you only have 1 or 2 rows that are null, you may just get rid of those rows. If you're somewhere in the middle, this is where this tactic kind of helps, because you still want the column, but you really got to do something. You can't just drop the rows because you're losing a lot of data. You want to try to fill those values, and you can try to accurately fill them, or as close to accurately as you can. So in this instance, we're trying to fill age with the median. That way you're not really messing up your distribution, but you're not losing that column altogether. So there's a lot of consideration that can be taken into here as to what you want to fill it with, to try to get it as close to accurate as you can. But for right now, we're just putting in the median age. So this whole part is just helping to get your data in a good format. And again, that's super important. You can't do any modeling if your data frame is not good. So you always start there. And then the next step with machine learning, right, is to go ahead and split it into your X and your Y. So that's what we're going to do here. And we're trying to predict survival. So what class is it going to go into, true or false? And then these are all the features that we're using. So male, right, is either yes or no, fair, second or third class. And so the reason we don't need first, second, and third is because if it's false for both second and third, then we know it's first. Right, so you don't need that extra column. That's something to consider too, because you don't want your data frame to be giant. It becomes confusing. You want it to be as small as you can while retaining as much information as you can. So you don't want to add unnecessary columns. So if there's a way to cover that, then that's good. So we don't add first class. This I think is number of siblings, number of parents. I think that's what it stands for. Kind of a weird abbreviation for that, but that's what that is. So then we're going to fit the tree again, similarly like we did before. And then once you make a tree, you fit it to your X and your Y, and we're going to plot this again. So you can see it looks really similar to that first example, right? It's making decisions. This one's interesting because the Titanics are pretty, I feel like most people know about the Titanic, right? And who the most people were that survived. So you can go through this and see if it matches your intuition. So the first thing it actually asks is, were they a male or were they a female? That was a really big decider, right? And who survived the Titanic, because they let women and children go first, right? So that's the story. So it's interesting that this data matches the story there. So that was a big deciding factor. And then I think, let me see where this ends up being. I think the left is girls. I'm pretty sure that it goes this way. I think false is this way. So then the next thing they ask is are they third class or are they higher than third class, right? And so this would be if you are So if you're less than third class, so if you're like a high class first or second class and you're a girl, you probably survived, is what it is. And so you can like keep going through and you can see the decision and see how the decision tree like found what you would guess would be true with a Titanic, which is kind of cool. I think it's neat that you can like see all the different options and plug yourself in. So that's what that would look like. This is cool. This is a thing that I really like about Google Colab, is you can make these forms, which, this is just nice. Like if you ever have someone that's non-technical and you want them to be able to play around with the model, they can do this without touching any code. But you can like, if you play around on my Colab, you can slide all these things and try to input this basically like inputs data and makes a prediction off of whatever you put in there. So you can guess like your probability of surviving based on whatever parameters you set here. So just kind of a cool little sliding thing that you can mess with. But like I said, decision trees are not just classification. So far, both examples we've looked at have been classification problems, but you can do regression too on it. So let's say with the Titanic data set, maybe we don't care who survived or not, but we want to guess how much they paid for their ticket. Well, that becomes a regression problem. But luckily, you don't have to change your approach. You can still do a decision tree, and it'll be able to tell you or give you an estimate for the fare. So it's the same step, right? You have to split into your features and your target. You instantiate the classifier, you fit the classifier, and then you see your results. Always the same. And so here you can see that now, just instead of it being a class, it's a value. And it pretty much does this just by assigning the mean. So it'll go about and it'll make the decisions again as to what it thinks is the best separator, and then it predicts the mean of everything that fell into that bucket. Does that make sense? So that's how it gets those values. So it does become numeric. It just takes a mean of the bucket. And that's how that works. It also, I think with anytime you do numeric data, instead of doing a Genie score, it does like mean squared error. So it's a different calculation of impurity when you're dealing with a regression problem versus a classification problem, but it's the same principle. It's still measuring impurity. So it's just different mathematically, which is also the nice thing. Machine learning inherently is very, very mathematical, but in order to get started with it, you don't really have to do any math, right? You just use these functions, you plug them in. So it's good to know the underlying math, but you also can like get started without that too, just knowing like what models go with what. So you can kind of do it at a higher level. Okay, so another really big topic with machine learning is this trade-off between overfitting and underfitting, and this is huge. This is kind of what I hinted at earlier with you don't want to have too many columns because that just kind of creates chaos. You're always trying to like find the perfect balance between the two. So here's a graph, but I'm going to describe them. So overfitting is when you make a model that is perfectly fit to the data that you have, but it cannot predict on data that's not in your data set. And that is something that you really run the risk of doing. Like you might optimize those parameters so well that you just 100% every time on your training data set, but as soon as you throw something to it that you don't know, like your model just does not work. And you can think of this almost like studying for an exam. Like say that you studied your study guide over and over again to the point that you can get 100 if your teacher were to ask you any of those questions. But more often than not in class, like your teacher's going to ask you questions that are related but are not actually the same. So if you don't know the concepts, you've only memorized the answers, you're not going to perform well on a test, right? It's the exact same with these models. Like they've basically just memorized how to get the answer, but they can't apply it. And underfitting is just like you just did not do well. You pretty much just take a guess all the time. So you want to find this balance of being able to like do well on your training set, but to extend it past that. And so that's always something that we're focused on with machine learning. I think this is like a good diagram of that too. So here's an overfitting one. Like it hits it on the head every single time, but like if you throw in something else, it's probably not going to fall on this line, right? Because that's not really where it goes. And this is underfitted, doesn't do well. This like is a little bit better. So, and this is how it affects prediction. So if you want to find this medium ground range, right, where it does well on your training data, it's probably always going to perform worse on your testing data. It just is because it's hard to like, you don't know what the testing data is, so you can't fit it as well to it. But if you come way down here where you're getting like perfect on the training, you're going to do really poorly on the testing. So it's just, you want to find the middle ground. So how do we do that? So there's something called test train split, which is a built-in thing to sklearn, which I haven't really hit on yet. Sklearn is a package in Python that has so many models. So most of the models that I've used in machine learning are through sklearn. And so same test train split is a functionality within sklearn. And what it does is it takes your data set and it's going to say, you can actually specify the percentage, but maybe you want to have 75% as your training data and 25% as your testing. It'll split it for you, give you your training, giving your testing, and then you can see that, right? You're not fitting it to all the data, so you can make sure that it doesn't overfit. So it's a really good preventative measure there. You can also hear, so this is how you end up doing it. It splits your X and your Y's, so you have to instantiate 4 variables for that. You run it through train test split, and then if you do stratify equals Y, it helps to make sure that it splits it evenly. So like if you don't do that, sorry, I'm getting a phone call. You might end up with like your training data set has all of one class and your testing data set has all of another. And then it doesn't really help the fact that you created a training and a testing because they're like so different from each other. So if you do the stratify on Y, that just helps make sure that it splits it evenly. So you have about the same percentage of classes in both the training and testing. So it just helps there. And I can show you what that does here. So right now we have made the X train, X test, Y train, Y test. And I can show you that overall, this is the percent that survived, and then this is the percent that survived in the training and testing. So you can see it's pretty close because we split the data set on that column. This is a good thing to do. And once you have that, we make a classifier. And then this is something we haven't done yet because so far I've just been showing you the graphs, but you don't really like show graphs to people. You need to show scores. So to do that, you can just do your classifier.score. This first instance, I'm scoring my training data. So I'm showing you how well it fit to the training. And that in this instance, I could run it again. It would be a different answer. But that it did really well. And in testing, it did slightly worse, but it still did pretty good, right? And that's a data set that you held out. So this is how you actually score your classifiers, is just to do .score. It's pretty intuitive. So like I said, the steps are always split it into training, testing, instantiate it, fit it, score it. It's really 4 lines of code, which is really cool that you can do something so powerful in like 4 lines of code. So an extension on train test split is cross-validation. So at train and test, you have one data set and you have one training and one testing, right? You just split it once. Cross-validation is test train split multiple times. So it makes it even better. It like gives you a more accurate idea of how it perform on different testing sets. So basically, like this graph is pretty good to show you what it does. Like the first round, this might be your testing, this might be your training, and it just keeps doing different subsets of your graph, as many cross-valids as you say. So like you'll just get to repeat this process on different training and different testing, and it just can kind of give you an idea of how you're doing overall because you're withholding different pieces of it. So to do this, it's also through sklearn. It's just cross-val score, and instead of doing the other stuff, so you actually don't have to fit it here. You just run cross-val score, and built into this, it does that. It splits up your data set into different sections, and it does it however many times you say. So here, I want to do 5 different ones. So that's what I'm saying here. And then you can print the scores and then print the mean score. So this is the output of all of them, and then it can give you an average. So it's just a better estimate. Test train split is really, really good too, but this helps you like help that problem a little bit better because you have more rounds of it. All right, random forests. Okay. If you want a really good video on this too, I'm not going to play it. We don't have time, but that StatQuest also has a really good video about random forests. But it pulls straight from decision trees. The difference is that this is what's called a form of bootstrap aggregating or bagging. But basically what it does is, so say you have your original data frame that you're going to take and you're going to make decision trees from. What random forest does is it wants to remake the data frame, and so it starts that by randomly subsetting rows. So it'll take random data values. So in your data frame, you may end up with like, I think they said about 25% of the data is repeated. So you might like not have 25% of your original data because you're just like randomly picking rows from your original. So you randomly subset rows, and then also when you go down here and you start making your trees, it doesn't look at all the options. So it doesn't say like if there are 20 columns, it's not like let me look at all 20 possibilities, calculate all of them, and then see which one is the best. It limits it. So you have random rows and it'll pick the trees based on like 2, 3, 4 options. So it's smaller in subset. So you end up with smaller trees because it's randomly picking rows, it's randomly picking columns. So like why would this be good, right? In theory. The reason, there's like some mathematical reasons with it, like you have a bias variance trade-off, but ultimately this can kind of be like the way I've heard it explained to me is almost like if you're wanting to pick a movie and you went and you asked all of your friends what movie you should see, everyone has probably seen a different subset of movies, and they probably have different things that they rate them on. Like, things might be important to different subsets of your friends. And so that's kind of what this is like you're going and you're making a bunch of trees that have seen a bunch of different data and they care about different things. And what you do is you get each result from each of those trees and then you average them together. So it's like a collective result. And so the reason that this is really good is just because it decreases bias. And so that's really helpful. It becomes more accurate than a decision tree because you're doing this. You're like making multiple trees and you're averaging them together, so it's more accurate. But the trade-off there is it's a little less interpretable, right? Because it's harder. You're not looking at one tree, you're looking at a bajillion and you're averaging them. So it goes in that trade-off. But random forest is the one, honestly, it's my go-to whenever I start a machine learning project. I do it with random forest. It's honestly kind of hard to beat. There are definitely like times that other things would be better, but it's just a really good one to start with off the bat because it's super powerful. So yeah, this is kind of what it does is you end up making a bunch of different trees and then you majority vote. So you go like pull each of the trees and say, what would you classify this as? And then you average them together and that's what you output. So it's random forest. And the way to do it is similar to what you've seen before. You get this random forest classifier and then you fit it and then you can score it, same as we have. And it does pretty well. So that's what you see there. You can also do cross-val score on it. That's what we show here. So overall, this random forest, I think it's fit. Yeah, it's fit on the same data that the decision tree is, and you can see it's higher. The other one was like in the 70s, and this is already in the 80s. So random forest definitely is more accurate in general. So that's what it is. Question?
Yeah, so that the cross-validation section, is that doing like the whole random forest all over again, or is that testing it with the split?
So it does run it every time. Yeah, so it has to split the data and then it fits the random forest model on each of those splits. So it runs it multiple times.
So yeah, the second box is splitting it first, and then right.
Yeah, so that cross-val score it does a lot. It's like built in, but within it splits, runs over and over again. Yeah, it's nice. It's all built in. All right, so another thing that we can talk about here is feature importance. So this also helps you battle the whole like overfitting versus underfitting thing is feature importance. And there's a built-in attribute which is cool to your classifier, just feature importances. And you can see like what it's using in the model, like what variables does the model rely on, and this can help you trim down your data set to what really matters, and it probably will predict more accurately when you have like the right ones, right? Because it's not being distracted by other variables that are in there. So it's a good thing to look at, especially if you have a really, really large data set. You want to trim it down and you want to use what's important. So doing this is a good way to do that, just to even get a picture of what it's looking at. But some other motivation for that. So if you select features according to importance, it's more interpretable because you have a lot less going on. It's trimmed down. It's also just easier to have fewer things. You don't have to clean as many columns. If you're like going and collecting more data, say this is in production, maybe you don't need to collect data on like 20 different columns if you're only fitting a model in 5. So it saves you a lot of money. It saves you a lot of time. And you also like don't need as many observations because you need like fewer observations if you're training on fewer columns. Does that make sense? So the like wider your data set is, the more rows you also need just to be able to train them as well. So it's just really good to kind of scale down and pick what's really important. So that's what we look at here. And then another way that you can make your models better is doing what's called hyperparameter tuning. There's a feature through sklearn that's called grid search that I've used before. There are some other ones. I'm not as familiar with them though. But what it does, this looks like a lot of code in here, but it's not that bad. But we import this randomized search CV. And so here, maybe you have a bunch of different parameters and you're not sure what the best value for those is and you want to test on all of them. So what this does is I can go and I want to say, I'm curious as to how this parameter affects the model. And you can give different numbers that you want to try. So I'm doing that here on a couple of different parameters, like number of estimators, depth, min samples, so on, bootstrapping. And you can put it in a grid. And when you put it in a grid, these are all the different combinations that I'm going to test my model on. So that ends up being a lot, right? Like it's 2 multiplied by the length of this, multiplied by the length of this. That's a lot of different times that you would have to run your model. And you probably don't want to run your model just once on the combination, right? You need to run it more than that so you can get an average of like what it's actually doing, in case one time it's just like a fluke and it doesn't do well. So what the grid search CV and randomized search CV do is it just optimizes that for you. Instead of you having to fit the model yourself like 100 times, it does it for you. So really nice to pass it through. And that's what this will do. So again, I'm doing random forest. I'm just making a random forest classifier. Then I have this search, and you pass in your estimator or your classifier, which we did. And then you can pass in those parameters that you're wanting to do, and you can say like how many iterations you want it to go through and so on. And if you do that, it fits it, and then it outputs what the best combination was. And so knowing this is kind of good before you like want to start and produce Model 2, because you can say like, oh, this is what worked. This is what I'm going to keep doing. This is how the model performed the best. So that's helpful to see too. So those last couple of things we talked about, right, are just all about optimizing your model. So they're really like the second stage. You fit a model first, and you're like, how can I make it better? Well, I can think about how to test, train, split, or cross validation. That helps you be more accurate. Sub-selecting different columns by feature importance. That's helpful. Looking at all the different parameter values. That's also really helpful. So these are all different ways that you can just make it exceptional. So. And with this, you can do like best parameters and then the absolute best score that you got here. So that's a good thing to do. I'll probably just skim through all of this because it's a little bit off topic from what we've got, and we only have a couple minutes. So I'll just give you a quick overview. But so now if you're thinking about how to evaluate it, we talked about accuracy, right? That's the big one that comes to mind, is how accurate was it actually on testing data. But you may not want to use accuracy all the time. So think about if you have classes that are really, really imbalanced and you do accuracy, that's just not really great. You want to do some kind of weighted accuracy because of that imbalance. And there are other things that you can look at too, like false positives, false negatives, all that kind of stuff. And then precision recall in F1. And I'm trying to see. Yeah. So a confusion matrix is that matrix of true positive, false negative, true negative. So this is something that you can look at with classification that may be a really good metric for you to use instead of accuracy, is to look at this. And in some instances, like it may be really important that like you don't have a false positive or that you don't have a false negative. So this is just depending on your case, these may be more effective for you than accuracy after you do your modeling to put it into something like this to analyze it with. So yeah, I guess quick overview. So you have on this column or on these rows, it's what you predicted, and then this is the ground truth. So true positive is when you predict positive and it's actually positive. True negative is the same but for negatives, and then false positive is when you think it's positive and it's not. False negative is when you think it's negative and it's not. So the definitions of those are, I wrote some like functions that would do that for y'all, and then some scores that come from that. So these, if you don't just want to like show a confusion matrix, maybe you need to show actual numeric scores. Precision is actually positive given that it was predicted positive. Recall is predicted positive given that it was actually positive. And then F1 is a mean of the two of those things. So these are just other scores. Again, sorry, not going super in-depth here, just a brief overview. But the takeaway here is that in classification problems, accuracy may not be your best metric, and so you can look at some of these other things they're like after you fit the model and stuff, that's how you would interpret it, is using these scores instead. So that is a overview of machine learning, and there are lots of different types of models that are cool to look into, but the good thing, again, in Python is that everything follows a similar format, right? It's all about, first data cleaning, then figuring out what you're measuring, and subsetting your data accordingly, and then fitting the model, scoring the model. Pretty simple and interchangeable without having to know too much of the details, which is nice. So, do you have any questions about machine learning, decision trees, random forests? No? Okay. You have a question?
In the industry, do you actually use the conceptual math?
I think it depends on what your job title is. So right now I'm working as a software engineer, so I don't need to know too much of the math, but I've talked to some data scientists who like actually are building their own models. And so in that case, like, yes, they need a lot of the math, So I think it depends totally on what you're doing. And that's like the interesting thing about working as a data scientist is every company defines it differently, right? Like their term data scientist may encompass something different at one company from another. Data analysts typically don't need to do as much math. It's a lot more like data manipulation, just fitting models. But if you're truly getting into data science and machine learning, then you probably do. Like if you're the people making the models, then that's when you would like need to know it. Does that make sense? So there's like lots of levels of how much you need to know. But and if y'all are curious about the mathematical side of it, this is a condensed course what I just taught. If you go on our YouTube, we had this course over a 2-hour block last year. And the first part is like ML part 1 theory. And then what I just taught is mostly ML applied. So if you're like interested in the theory behind it, we have a lesson that's like all theory online. So, question?
If you're a TAMU student, do you have any classes you would recommend?
Oh, okay. Let me think. It's been a couple months. There's a stat class for data science and data science. I think it's stat 335. That was a good one. It was really applied, which I liked a lot because I got to just go through Python and learn about that. I also took computer science 420 and 421. 421 was machine learning, so it was good. You learned a lot. 420 was AI, so it's like related, but it's not quite the same. 421 is like the machine learning one. And then I also, if y'all are interested in reinforcement learning at all, that's really, really cool. I took a special topics in computer science over RL, and I loved it. So that's also a really cool area to look into. And then if you wanted, like, understanding the math behind some of this is really important too. So, like, I took some, like, stat probability courses that I thought were really, really helpful, like stat 414 and 415. Yeah, there's also a ton online. I think that's the one thing I hope we see more from at A&M in the future is I think a lot of my learning that I did for this was online and on my own. And so I think they're working on like putting together more data science curriculum is what I've heard. So I'm hopefully like they'll come out with some of those for y'all. That would be cool. Yeah. Right. Any other questions, George? Yeah. Thank you guys. Y'all should have access to this and the data science. And again, I tried to make it like as clean as I could so that you could like go in and click on whatever you're needing to see so you can reference it. But if you have questions as you're doing a project, come and ask. And I encourage all of y'all, even if y'all are just starting out with this, give it a shot because you'd be surprised with what you can put together. And we have a lot of us here that are like, we are here to help. And like a lot of us have even driven in from out of town to like be here to help y'all this weekend. So we want to do that, and we want to encourage y'all in your journeys. So, like, don't be afraid to ask questions and get started. So, yeah. Thanks, guys.